Hi, in this webinar we're going to investigate Hopsworks.ai as a platform for doing feature engineering. Hopsworks.ai is a cloud-native feature store that supports computation of features and storage of feature data in a feature store. So my name is Jim Dowling and I'm going to go through this with you. I'm going to start by defining features from a data engineer's perspective. So data scientists will be intimately familiar with features, and data scientists, I'm going to open a pen here, data scientists know that features are fed directly in to train models. Models are used to make predictions in machine learning. And data engineers will have a slightly different picture of what a feature is. So data engineer will see some data in their back-end platforms. So they might have some operational databases or some data warehouse. They might have a data lake. The data will often have schemas. Sometimes it will come in files and it'll be unstructured. But what data engineers have difficulty is understanding sometimes this transition or transformation of the back-end data into a numerical representation that can be used directly in models for training those models, but also by operational models that need features to help make predictions. So operational models may need to say, hey, I need some historical features or some contextual features. Can I please get them because I need them in order to build something called a feature vector with which I can make predictions with. So things like varchars, which are strings ultimately in databases, typically we're going to encode them in something called one-hot encoding, which is a common way of encoding a varchar. And that's in a format that can be used directly in the model. So it will be a numerical format for that data, and that can be used to train a model. So there's a gap between the data engineering on the left and the data science on the right. And we're going to investigate some of that. And we'll do it with a very simple example of feature engineering. I could give you a definition of a feature as being some entity under observation that helps you build predictive models, so it has some predictive quality to it. And the feature that we look at here is called the load factor for a room for a given month. And you might understand that, yeah, if I know the load factor for a room, I can make lots of different predictions. I can predict things like what's the probability that this room will be free in a given period of time. I can help predict the revenue in a given hotel given the set of all load factors for all rooms. I can help predict when's the best time to do things like maintenance on the hotel, and load factor will be lowest. There's a lot of different things you can do. So what that means really when we translate that into what we're talking about, which is feature engineering in a feature store, this feature, the load factor in the hotel room, can be reused. We want to reuse it in many different models because we think it'll be quite useful in different predictive models. Now that load factor you won't find probably in your existing operational databases. What you might find instead is some raw data. And that raw data might have, for example, the bookings. And the bookings might have a start date, an end date for a booking, a room number. So in this case we can see the start and end date were the 22nd and 27th of May 2020, and the room number is 23. But if I want to compute this load factor feature, I'll need to examine this raw data. I'm going to have to write some code or have some logic which will compute the load factor, which will be the sum of all of the nights that that given room was occupied in the month of May divided by the total number of available nights in May. That will give me the load factor. And this feature transformation, typically we're going to say it's going to be some code. Now in some cases you might be able to have a domain-specific language, a DSL, or you might have UX support for defining this DSL. But in this webinar, we're going to concentrate more on programming language support, in particular Python. And I'll get to the motivation for that soon. And obviously SQL can be used for simple examples, but we'll see how Python gives us a richer support for doing these feature engineering or data transformation steps. So feature engineering is about transforming your raw data into these features, and this is a very simple example. If we take another example, which will be less intuitive, where we have some raw data, and the data is already in numerical format, and a data engineer might believe that this data is in good enough quality to be used directly in a model. We have numerical data, but the data scientist might say, well, hang on, these features here, they're not there's quite a wide spread between the numbers. I think it might be numerically unstable in my algorithm. So what I'm going to do is I'm going to take these features and normalize them. And I can apply something called the L1 normalization algorithm to those features to compute them. What it will do is squash those feature values into a given range. Typically that range might be between 0 and 1 or 0.5 and minus 0.5. And what also is challenging from a data science or data engineering perspective is, what if I have to do this at scale? What if I have maybe millions of rows or billions of rows, and it would take a very long time to do this, or might not even be possible to do this on a single machine? Well, in that case, you can use Spark or PySpark. If you're in Python, you might say I'll use PySpark, which is a framework for doing distributed computations. In this case, the computation we're trying to do is feature engineering. And we can see some example code down here, which is basically reading up our raw data from a Parquet file as a data frame called scale_df. And then we're going to apply this L1 normalization. We have this normalizer set P1, and that's going to apply this feature transformation code to that data frame. And it's done lazily. So when you call transform, it will apply it to the data frame. So feature engineering can be done at scale with PySpark, and we can still do it in Python. But some people think, well, SQL is enough. I can take my raw data, most of my data is in a data warehouse. I can take that raw data, I can convert it into features, and we can train models on that. And for some use cases, that may be the case. But as a general purpose platform, SQL has limited support for the kind of aggregations that you want to do for computing the features. The data sources are pretty much limited to data warehouses, databases. And then finally, we're going to see that there's limited support for data validation in SQL. So data validation is where a schema is not enough. So if our features are all numerical, that means the schema the data is 32-bit floating point numbers, for example, or 16-bit floating point numbers. That doesn't help us tell us whether a given number that comes in is a valid number, because maybe that data, for example, it could be the age of a person. That age should be between 0 and 150, let's say. And if an age of 10,000 arrives, it's a valid number from the SQL schema perspective. But from a data validation, it's bad data that's coming in. So you would like to validate the data that comes in, not just based on its schema, but also on valid ranges of individual feature values, but also on things like whether a feature is unique or whether a feature has null values or empty values. There are a lot of different what we call data validation rules or predicates we can apply to our data to ensure that that data is correct. And that type of what we call data validation rule is different to what you might think of as a unit test for the feature engineering code. So the unit test for your feature engineering code is about ensuring that your transformation, the feature engineering transformation you made, is correct. It's doing a correct transformation of that data. This is a data validation rule is about ensuring that the data that comes in from the back end is correct. And there are two slightly subtly different ways we want to test our data before it comes in. We want to test our logic for transformations correct. We also want to ensure that the data coming in is correct. And that's why we're going to talk mostly about Python in this webinar. The Hopsworks platform also supports Scala, so you can do all of this at Scala. But more shops are now using Python end-to-end, and it's growing in popularity relative to Scala, so we're going to concentrate on Python for doing end-to-end feature engineering. One of the advantages of Python over SQL is, of course, it supports many different data sources. You can have unstructured data from files, you can have structured data from databases and data warehouses, you can go to Kafka topics, and you can pull data from all these different sources. Similar to SQL, there's very good support for libraries for doing feature engineering, so transforming that raw data into features, and we'll look at a few libraries in a second. And there are also libraries that explicitly support validating data, so defining data validation rules so that you can ensure that the incoming data is correct. Okay. Okay, let's move on. So before I move on to talking about those libraries, I'm going to introduce the Hopsworks feature store. And the Hopsworks feature store is built on three different concepts. One is the notion that there are features available for data scientists, and those features come together in groups. Data scientists will look at these features and can basically join features together, can pick different features from different feature groups and say, I would like to create training and test data from all of these features. So in this example I have here, we assume there are two what we call feature groups. Think of them as two different data sources where the data has arrived from. Maybe they're updated at different rates. Maybe they come from different platforms. So the Titanic passenger list is a well-known data set from data science. The idea behind it is often that you're going to train a model to predict if a passenger survives or not. And there's a number of features. So important features that help predict whether a passenger survives are the sex of the passenger. Is it male or female? Were they first class or third class passengers? But in this example, we're going to assume that some historian has come along and done some research and found out the amount of money that the passengers in the Titanic had available in their bank accounts at the time the Titanic sunk. And the idea is to bring in this data from some place. This is coming in from some nice library or museum. And this data can help predict whether a passenger survived in the Titanic or not, because the assumption here is that it might tell us whether that passenger bribed to get on a lifeboat or not. So the data scientist who has this hypothesis can basically join together all of these features, and in this case they just pick out the features from the different feature groups. The query planner in Hopsworks will attempt to find a common join key. In this case we'll join on the name of the passengers. So if you want to join features from different feature groups together, there should be some common join key, some entity. It might be a customer ID, it might be a session ID, it might be any kind of identity or time that you use to join these things together. And once the data scientist has decided on the training test data set they would like to build, also a validation set as well, they can say, well, what am I going to do with it? Am I going to work with it directly as a pandas data frame, or am I going to store it as a TF record because I want to train a model in TensorFlow, or as NumPy files, I'm going to train a model in PyTorch, or CSV files, I'm going to train a model in scikit-learn. And then where am I going to save that particular data? And in our case, we can save it on Amazon S3, and that's what we're going to look at today. We're going to look at working with S3 as a store for training data for your models. Okay. So what we do in our particular feature store is we version all of these three abstractions, the features, the feature groups, and the training test data sets, because we want to be able to reproduce training data sets. We want to be able to know, okay, this model was trained by this notebook, and here were the dependencies of the notebook, and it trained using this training data set. What were the versions of the features for these different feature groups that were included in this training data set? And this helps you reproduce your models, which is important for governance and so on. So before I move on, I'm going to just bring together what we've introduced, feature engineering, so where features come from, and the feature store. And I'm going to do it with the help of this feature group abstraction I talked about. So I mentioned already that data can arrive, features can arrive from different sources, but we didn't say too much about what those sources were. We said that they might be a data lake or a database or a file system, but what I didn't mention is that features may be updated. The raw data for computing the features may be updated at different cadences or different rates. Some of them may be updated very frequently, and some of them may be updated very infrequently. So you might have data sources, for example, that if we take one example that we're working with is users enter data into a form on a web page. So maybe they're applying for a loan or insurance or something like that. And we need to take that data and transform it into features. And we need to do that with very low latency. So we need to do it within a couple of seconds, for example. Other features that maybe will arrive are the users clicking on web pages, changes to databases, updates to data warehouses. They're not going to arrive as frequently. Okay, they might be updated every few minutes, every hour, every day. So here's some examples. I gave the example of the 2-second one because that's one we have experience with. But you'll have other ones with relatively low latency. So if you want to get the clicks that a user is performing on their mobile phone, well then you might push the updates to all the clicks they've made every few seconds, every 10 seconds, 5 seconds. If we want to get the changes in an operational database and push them to the feature store, we could use the CDC, the Change Data Capture API, to your operational database, and then all the transactions that have committed in the last 30 seconds we push together and compute new features from them and then push them. So typically, because of the low latency here, we'll need to run a streaming app to do this. You couldn't launch a batch job to capture the last 30 seconds of CDC data from an operational database and push it to an external system, because batch applications can't run that frequently in a shared cluster environment. However, if you have an app that's going to run once an hour, now you can run a batch application. It could be a Apache Spark, or it could be just a Python Pandas application that will check for updates to, for example, user profiles, and then just push those as new features to the feature store every hour. And you might have other changes which happen even less frequently. So maybe, for example, you have web logs that you compute features from, and just once a day you update them to the feature store. So these are all feature pipeline examples. And if we look at them, we can see that most of them, I just pushed back, I went one too far. Most of these features go to the feature store. So what we're saying is this data will be cached in the feature store. So we'll have features related to how many clicks users have done, the change data, capture data from external databases, user profile updates, weblog features. We'll put them in the feature store, and then online applications and users who want to create training data sets, but also batch applications that want to get features to score them. So maybe you have a marketing application that wants to get information about users and how often, for example, they update their profile as one of the features, and they're going to then score users basically based on how which is the most attractive to send this next marketing campaign to. Now if we take the online application up here, this will need to look for historical features. So if we have something like how many web clicks the user has done in the last 10 seconds and how many they've done in the last minute or last hour, maybe updates to their shopping cart or basket, basically anything that's contextual, that's not going to be stored inside the online app itself, can be pulled as a feature from the feature store. Features that can't be pulled directly because we don't have enough time. The user enters it on the website, it needs to get to the model in less than 2 seconds. We won't be able to push that directly to the feature store, so we just make it available to the online application directly. And one of the problems we have here with this setup is that we have different consumers. The online apps, they need very low latency access. And then the training and batch applications, well, what they need is they need scalable amounts of data, very large amounts of data. There's not really any database that gives you both of those, meets both of those requirements. And if we add into that the requirement to reuse features, so reusing features means effectively that you want to join features from different feature groups together. Now, if we didn't join the features from different feature groups together, we'd basically have redundant copies of those features. But in our case, we do. We would like to reuse these features. So by virtue of that fact, there's no real database that's out there that meets these requirements, that has low latency, supports joins, and scales to terabytes or petabytes of data. So what typically people do is that people who've built feature stores is they'll have one database for low latency access to the features and a second database for scalable storage of features. We call this a dual database setup. In our case, we use NDB or MySQL cluster as our online feature store, and then we use Apache Hive on HopsFS, our file system, as our offline feature store. And we also support Hoodie on top of that to enable something called time travel for feature groups. Now, another point of complexity that's introduced here is that previously we just said we were pushing features to the feature store, and now we need to decide, will this feature go to the online, the offline, or to both? And now potentially this code that you wrote to transform your raw data into features needs to be aware of which features have been pushed to which feature store, and what happens if we have failures. If we've written to one feature store, the job fails, and we have to restart the job, or the job gets restarted automatically, how does it know which one it's written to? So there will be a lot of complexity introduced by this dual database setup, and that's where Hopsworks comes in to help you. So Hopsworks provides a data frame API so that applications don't need to worry about, what happens if the online feature store fails while I'm writing, or the offline feature store is temporarily unavailable. Applications use data frames to capture the changes that they want to push to the feature store. So maybe they're creating a new feature group, or maybe they're updating a feature group. Well, in that case, they might decide, I'm going to get my raw data, compute that data into a data frame, and then do an upsert into my feature group. Now, if that feature group should be available in both the online and offline feature stores, fine. You just, when you create it, you say this is online and offline, and the complexity of managing the synchronizing of that data frame to both online and offline is managed by our platform. So what type of applications can you do in this can you write in this setup? Well, you can write classic Spark applications, so Scala Spark, Java Spark. You can write PySpark. You can write pure Python applications with pandas data frames, and you can also have streaming applications, so PySpark streaming applications, and all of these natively support data frames that they can push to the platform. Flink, in this case, we need to work around a little bit because it doesn't have a pure data frame API, but we can still push updates to feature groups as Parquet files. So in the real-time feature transformation example, what we do, and we're doing with one customer, is we use Flink to do the very low latency transformation of data, so that in data features arrive in a Kafka input topic, and we write the output to a Kafka topic, and the application can receive that in very low latency. But otherwise, the online applications, we'll see later on, will use JDBC API to get low latency access to the features in these feature groups. And then the training applications or batch applications, we use Spark to join features from different feature groups together and either work with data frames or create training test data. So what we've introduced in Hopsworks is, to summarize, is we simplify the ingestion to this online and offline feature store by providing a general purpose data frame API along with this feature group abstraction that makes it easier for users to reason about where the data is coming in. So let's have a quick look at code for that to make it a bit more concrete. In this example, and this is the example I'll cover later on in the demo, what we're doing is we're going to read data from a bucket in S3, and this example is about customers of a telecom company, and we're going to try and predict if that customer will churn or not. Churn means that they're going to go from a current subscriber to a non-subscriber state. Now, this data we're reading up into a pandas data frame. This telecom is a pandas data frame. To do that, we'll need a library S3FS, and we'll also need the Hopsworks feature store because we're going to create a feature group using that data frame. The example has quite a lot of feature engineering in there. Just to give you an example of the kind of feature engineering steps that you might take, you might say, in this data frame telecom, for the column total charges, that's a feature in there, we'd like to replace empty strings or spaces with, in this case, null values. And there's many more steps and examples in the example later on. Okay, so that particular example showed you how to do a little bit of data transformation. It didn't do data validation, and I mentioned earlier that the typical steps that you have when you're taking your raw data, and this is our raw data here, is that we want to transform that data. So we want to take numerical data, maybe normalize the values, zero mean them, varchars we want to one-hot encode, and so on. But we also want to validate the data that came in. Now you can do all this in one program, or you can do it in two separate steps. It's up to you to how you want to design your pipelines. But what we'll look at is frameworks that help you both feature engineering or data transformation and data validation stages. So you need at some level both of these steps before you ingest your data into the feature store, because then data scientists can be happy enough knowing that the data or features they're going to consume to train their models will be correct. They won't need to waste or expend the 80% that we typically say they expend on doing data cleaning and data transformation. We expect that will have happened before the data arrives in the feature store. So let's look at some feature engineering frameworks that are out there. If you're just working with Python as your main programming environment, so you're going to do your data transformation in Python or feature engineering, Pandas, of course, is widely used and massively popular. Another good open source framework is Feature Tools, and we can have a quick look at that web page for a second. We also have support for when we go to distributed Python. If we want to do our feature engineering on more than one server, you can do Dask or PySpark. Our platform Hopsworks currently supports PySpark, not Dask. If you're going to leave the Python ecosystem, you can use Scala and Java with Spark. You can use Flink. And if you're going to work on just Google Cloud Platform, you can run Beam on top of Dataflow in their particular cloud. But let's have a quick look at feature tools. Just going to open up there. If we look at feature tools and GitHub, we can see here the web page for it, and you can pip install it. It's available on Conda Forge channel. And the kind of things you can do is you can read up your data. So you import feature source FT. They have an example here where they show you how to do some feature engineering on transactions, sessions, and customers. And I'll leave it to you as future work to figure out how to use this. But it's a relatively useful framework for feature engineering. We're going to look at some concrete examples of Pandas in a little bit. So after you've done your feature engineering, you can do data validation. It can be part of the same pipeline. It's up to you. So the frameworks that we think are very useful here, if you're in a single host Python environment, Great Expectations is an open source library, and it's very useful. I'll have a look at that on their webpage in a second. If you want to do data validation at scale in Python, there's really only one framework we're aware of right now, which is TFX, TensorFlow Extended Data Validation. It runs only on Beam. So it's not a general purpose framework that will work in any environment. We have very alpha support for Beam on our platform, but we're not going to go through TFX data validation. Instead, we'll look at a framework called DQ, and DQ was developed by Amazon, and it runs natively on Spark. It only runs on Scala Spark. It's not available, unfortunately, for Python. Now, Great Expectations also does work for Spark, but it's not as natively integrated with the Spark data frames, so you have a lot more work to do. So what we'll look at in Hopsworks is that you can actually declaratively specify in the user interface data validation rules that will get executed as DQ. So data scientists in shops who like Python and don't want to include Spark code in their pipelines can actually define their data validation rules declaratively in Hopsworks, and then we'll convert that into a DQ program that will run as part of a pipeline. So I'm going to demonstrate that later. But what I'll do before I demo that later, what I'm going to do is just move back and we'll have a quick look at the web pages, which are quite good. So if we look at Great Expectations, we can see a couple of examples of how you write code in Great Expectations. You can see that when you have a data frame, you can basically write something like the following: expect column values to not be null. You can say expect column values to match a particular regex, or the median to be between different values. So it's quite a declarative way. You can see here, that one jumped a little bit. Okay. I think I clicked on it by accident. So expect column values to be between, and here's the name of the column, and the min and the max value, and then mostly, which I'm not exactly sure what that is. At least 95% of the time. Okay, so it's allowing for a certain number of values that deviate from the min and max. So 5% of the values can be outside the range 60 to 75. Okay, and you're just going to get a warning. So you can also and you get this nice user interface, a HTML page back as a report of the data validation rules. So the other one is AWS DQ. DQ, which is also on GitHub. And this is the one we'll look at in a little bit more detail. So DQ is actually a very efficient library for computing statistics and on Spark data frames, but it also has support for these declarative data validation rules. So if we look at this example here, we can see that we have this data frame called data, and this is the data frame here that's being read up. And this particular piece of code, it's in Scala. What it's doing is it's saying for this data frame, we're going to have a check, and if the check isn't correct, we'll report an error. It also supports warnings, but the checks are the following. There should be we expect 5 rows in this data frame. This ID column should never be null. It should always be unique. The product name should never be null, and so on. We can see these are the declarative rules that we define on our data frame, so that we can apply them on feature groups in Hopsworks. So let's keep going. Okay, so yeah, so that's the data validation rule. So what we've looked at so far in our feature store is we've looked at how we ingest data from different backend systems, frameworks for doing data feature engineering and data validation, ingesting that data into the feature store, and we'll briefly look now at how we can access that data for creating model training or training test validation data sets, and how online applications can use that data. So we'll start by looking at how to create a training data set, training test validation data set on S3 in a bucket. So what we can see here in this small code snippet here is that a user has a little piece of code that's saying feature store, get me these features and join them together into it, and you get back a data frame. So what will happen is a Spark program will actually run that will identify the largest overlapping set of common primary key columns between the different data frames involved, the different feature groups involved, and it will then join those together and you'll get back a data frame. So you can then save or materialize that data frame in a file format of choice to, for example, S3. So this code can run locally in Hopsworks, or it can run on Databricks. You can use Hopsworks from a Databricks environment, or you can use it from SageMaker. If you use it from SageMaker, SageMaker is not a Python or Spark environment. It's a Python environment. So what it will do is it will run a job on Hopsworks that will do the join, because the job itself will be a Spark job that will do the join. We're using Spark as the join engine for joining the different features and feature groups together. So a few things we need to do, and we're going to do when we get to the demo, is we'll need to add support for some libraries. One example library we have is if you're using pandas and you want to read from an S3 bucket, you should add this S3fs library, and then you can just call pandas.read_CSV, for example. And in recent versions of pandas, you don't need to do anything else. You can just call that directly, which is nice. We'll have to install some other libraries. We'll also need to create an S3 bucket a connector in our feature store, because we're going to try and write out data from to an S3 sync, so an S3 bucket. This one's called SageMaker Gym, is the name of the bucket I have already. And this is the more complete code that would be used to create the training data set on S3 using our feature store. So we saw this example earlier on, and it returns a data frame called sample data. So to store this data frame as TF record, we specify the sync as being our S3 bucket, the connector to our S3 bucket, SageMaker Gym, and then we can optionally give a version to the training data set. It'll pick the one by default if you don't specify it. This is the name of our training data set, and then this is the data frame that we are going to create the training data set with. Okay, so that's a brief introduction to Hopsworks, the feature store. And Hopsworks itself is a little bit larger than the feature store. So this is our feature store here. And the feature store stores its data on HopsFS, and HopsFS in turn on AWS will store its data in an S3 bucket. But we also can run compute on Hopsworks. We can run Spark, Flink applications, Python applications on external Kubernetes cluster if you want. We also support training of models, running Jupyter Notebooks, even running Jupyter Notebooks as jobs, and then using any library that you can pip install, from TensorFlow to PyTorch to scikit-learn to XGBoost. And the platform also supports model serving, so you can serve models on Kubernetes clusters, and we can monitor those models as they're running. And because we have many steps involved in many of these different training pipelines, but also in the feature engineering pipelines, we support Airflow to orchestrate those different steps. And we have Kafka support as well for ingesting data, but we also use Kafka to monitor models. The predictions sent to models or sent from models are logged to Kafka, so that you can monitor them in real time if you wish, which you should. So how does this all fit together? Hopsworks provides a bit more. It supports training and serving. But the three parts that we see as it all fits together is we have this feature engineering step, and that's taking our raw data, making that data available as features on the feature store, and then data scientists can come along, grab those features, and turn them into models. So the features are coming in here, and ultimately they're being transformed into models after we've trained models. So we take the features, combine them into training test data sets, train our models, validate and analyze those models to make sure they're correct and have no bias. And then when we're happy with them, deploy them to our model registry or repository. Models can be made available to batch applications. They can use them directly to score models. But also you can deploy them to an infrastructure for serving models, so a model serving infrastructure that needs to do monitoring of models. But also what you want to do is, and I mentioned this already, online applications sometimes will not have all the features available to them locally. They might need historical or contextual features that are in the feature store. So either the model serving code itself or the online application can look up features that it's missing. So it'll pass in IDs, for example, for session carts or users or timestamps, and with those IDs or keys we'll look up the other features that are not available in the online application but were used to train the model, so that we get the entire feature vector that was used to train the model. We get the online or real-time version of it that we can now send for prediction to the model serving server. So these are three parts. We have the feature engineering, we have the model training, and then we have the online model serving. So Hopsworks supports all of that. We also support scalable training, so multi-worker training, and we use PySpark to distribute that training. We support asynchronous hyperparameter tuning on a framework called Maggie, as well as parallel ablation studies, where we can in parallel run lots of different ablation experiments to test what different parts of the model, how they perform. So, you know, if I remove a given regularization component or add a different layer, how does that affect the performance? So doing that in parallel enables you to do it faster. The platform also supports something unique called project-based multi-tenancy. What this is effectively is what's called dynamic role-based access control in the security world. What that means is that you can have sensitive data, put it in the cluster, put it in something called a project, and then give somebody restricted or sandboxed access to that data. And we know when the user processes the data in that project, they can't copy the data out, they can't read data from other projects, even if they're a member of the other projects, they're going to lose the capability for that. And we do this by basically creating a unique user identity for every project. So when you're running code in a project, your identity is not your global identity, but a project-specific identity. So if I have a project called Churn, well, my identity will be Churn Jim. And when Churn Jim tries to read from another project called Churn Finance, or called Finance, well, it's a different user. It's Finance Jim, and I'm Churn Jim. Now that's useful in that you can sandbox, but we also want to be able to share data across projects. So the actual data sources we support for this multi-tenant sharing across the different projects are data sets, that is subtrees in our file system, so our next generation HDFS called HopsFS, databases in Hive, feature stores can be shared. So if you have a development feature store, a staging feature store, a production feature store, it's often very useful to, when you're developing new features, to share the production feature store read-only with the development feature store. So that means that the person developing the features can test out joining those features with production features to make sure that everything's working correctly before they then migrate those features to staging and then later on to production. You can also share Kafka topics, which are private to projects. It can be shared across projects. And each project then has its own Conda environment. So one of the challenges for Python developers in any platform is how do they add new libraries, remove libraries? Well, we provide a Conda environment per project, so users can install libraries, remove libraries, and they don't need to write Docker files. They can just do it from the user interface, and in the background we'll take the Conda environment that you've created by adding and removing libraries and build a Docker file based on that. So when you create a job, you can then pin that job to that particular Docker file that your state of your environment at that point, your Conda environment at that point. But then you can keep obviously developing that Conda environment as you develop new models and so on. So and that's very much part of the ML Ops support in our platform. We also support something called implicit provenance for ML workflows. What this basically means is that when you start from your training data and your features, so we have features that go to training data that creates models, we would often like to traverse that in a reverse direction. We have a model maybe that has some bias in it, so let's go back and identify the program that was used to train it. Let's identify the training data set used to train it. Let's identify the features used to create that training data set. So we want to often navigate this over and back for debugging, for governance, for regulatory reasons. But we do this with by adding support for implicit instrumentation of your existing pipelines. So as you write to our file system and you say, hey, save this model, we'll have an event. We have a CDC API to our metadata layer. It says, hey, a model was saved in this project, and we add that. You don't explicitly need to write in your code, I'm saving this model to this particular location. We do it in the background for you. So in that case, it's pretty much an alternative to TFX or MLflow in terms of managing experiments and this provenance across the different stages in your workflows. Now, if you want to try out Hopsworks, we have this managed SaaS platform on AWS called Hopsworks.ai. There's a community, a free open source version of Hopsworks. It's AGPL v3 licensed. It has complete it's fully functional from a feature perspective. There is an enterprise version which has connectors to external Kubernetes clusters for model serving, running notebooks, also for Active Directory, LDAP support, and GitHub support. But the community version is open source, and you can do pretty much everything that you can do in Enterprise Hopsworks except these connectors. I'm going to go through a demo now, and I'm going to do it on Hopsworks.ai. Hopsworks.ai is currently free to use. You can register and you can run clusters, and you won't get charged for the next 3 months. And the example I'm going to run is a churn model for telecom users. So we're going to try and predict if a particular user is going to churn, is going to go from the state of being a current customer to being a non-customer. The data set we have is stored in a bucket in S3. We're going to create a feature group from that. We're then going to train a model using that training data. We're going to create the training data from the features, and then we're going to train a model using that training data. It's based on a Kaggle notebook and also a Feast notebook, a notebook in the Feast project, which is a different feature store. And the code is available at jimdowling/churn. Okay, so let's get to the demo. So we're going to use Hopsworks.ai. That's this particular platform here. And you can register for a new account here. I've already logged in. Registration is pretty straightforward. But when you come in here, you have to set up what's called a cross-account role if you want Hopsworks.ai to launch a cluster in your AWS account. You will have access to a demo version of Hopsworks where you can just connect in and try it out. But if you actually want to test the platform out with your own data sources and your own data, then we recommend setting up this cross-account role. And to do that, you can see there's 3 steps. You need to create a cross-account role, so you follow these steps here. You need to add an inline policy to the cross-account role, which will allow us logical clocks or Hopsworks.ai to launch EC2 instances in your cluster, and then you need to store this cross-account role here so that it becomes available to Hopsworks.ai. So the details for this are available on our help, hopsworks.readthedocs.io. So I'm not going to go into too much details, but if you click on Getting Started and you click on Hopsworks.ai, well then what you can see here is it walks you through how to connect your AWS account and create these cross-account roles. Okay, so let's assume you've completed that step. And we go back to our dashboard. So I've already run a cluster, but I'll create a new one just to show you what's involved and what we need to do. But before I do, I'll just explain this cluster that's here. I have a URL to it. This one I created a user automatically by my email and generated a password for me. You can also use LDAP, so you can connect it into an LDAP server that you may have already to allow users of that LDAP platform access to Hopsworks. What we can also do is we can take the feature store, the online feature store, our Kafka and SSH services on this cluster that's running and make them available to other, for example, Databricks or SageMaker. If you want them to access the feature store, well, we deploy this Hopsworks cluster in the same VPC and subnet as Databricks or SageMaker, and then we expose these services, and then they become available from within Databricks or SageMaker. There are webinars you can read up on that. We have separate webinars on Databricks and SageMaker where you can find out how to do that. You can make backups of your cluster. You need to stop the cluster to do that. So you can stop and start your cluster at any time. And then there's some more details here on this particular cluster. So let me show you how to create a cluster, because this is kind of important for if we want to read and write to S3 buckets. So we'll call this one Webby. And I can store the data for this particular cluster in an S3 bucket if I want. I'm just going to skip. You don't have to, but typically if you want to save money, you would store your data there. So that means HopsFS will be connected to an S3 bucket and store its data there. If you don't, it'll store it on the local virtual machine, which is going to be EBS storage. Now this is the stage where the Hopsworks cluster that runs, I'm going to give it an instance profile. So an instance profile is an S3 role, and if this particular S3 role, HopsFS S3 access, allows me to read and write to my SageMaker Gym bucket. And I want to be able to do that because I'm going to run a program on this cluster that reads from that bucket and also writes to that bucket. So this is the way the programs that run on Hopsworks will then inherit those privileges. You put it in a VPC and a subnet within that VPC. You can create a security group, and we're not going to use LDAP. And that's the summary of the cluster I'm going to create, and I go ahead and create it. Now, it takes a couple of minutes, maybe up to 4 or 5 minutes for that cluster to actually become available. So I have one running already. So I'm just going to open it. So it's using username, password, login. So when I log in, I have these projects available here. And the project, as I mentioned before, consists of some users, there's some data, and some programs in there. And they're private, so it's a sandbox. So I ran this demo already, but I'm going to rerun it again from scratch. So what I'm going to do is I'm going to just create a project called Telecom. Now there are a bunch of services here, and you don't have to pick all of them. If you're just working with the feature store, you can pick just the feature store, but in this case I just took all of them so we can get a quick overview of what features are available in Hopsworks. We have these tours here on the left hand side, so if you're going to start out in the feature store, you can run the feature store tour and it'll create a bunch of feature groups that you can play with. And if you want to try out deep learning or Spark or Kafka, you can run those other tours. So I created one called Telecom, and I'm going to start by installing the libraries that I need. I think one of them was S3FS. So I'll show you how we do this. So we basically go down to this Python service on the left. We have a bunch of services here on the left. We can see the cluster utilization, members. Members just shows you who's in the project, and you can add and remove people, change the role from data owner to data scientist. I think S3FS is available in Conda. So let me search for it there. Yes. So this is how you install a library. You basically search in either Conda or pip. and then you press install, which is pretty user-friendly for data scientists. So I'm just going to look up the other libraries that I need to install. They're in this GitHub repo in this file called install pythonlibs.txt. So there's 7 of them. Now I could have made this available as a YAML file and just remove the existing base environment and install the new one, but I'm just going to go through it by hand because it only takes a few seconds. So I'm just installing libraries using Conda first, and then I'll move over to use pip. So, oops, I'm going to give that the correct name. So if you have a library, for example, in Conda Forge, well then you just edit this and type in Conda Forge and save, and then search, and it will access Conda Forge instead of the default Conda version. So for pip libraries, I change to the pip tab. So Yellowbrick is not available on Conda currently, and the other libraries are Slugify and Imbalance Learn. So our last one, Imbalance Learn. Okay, and that's it, we're done when we do that. Okay, so now we've installed all the libraries. Like I said already, an alternative way to do it would be, and these are the base libraries that you create, we have in your default Conda environment. So, you know, we've tested all these libraries together. You have Pandas, PyTorch, NumPy, Maggie for hyperparameter tuning, Hops for feature store, and so on. TensorBoard, TensorFlow. But you can also remove that environment and import your own Conda environment if you want. In this case, you can see the libraries that I've been installing are currently being installed. It goes pretty quickly generally. And when they're finished, you can use them. So then the last one there is Imbalance Learn. And you can click on here to get more detail. In particular, in big clusters, that can take, you know, a few more seconds to install on all the nodes in the cluster. What will happen in the background is when you've installed new libraries, it will compile a new version of the Docker file to run, because later you might want to run a job based on the current Conda environment. And it'll pin your environment by creating a Docker file from the current set of libraries installed. So I'm going to now, rather than go through all of the other, we can see there's a bunch of other services here. I'm just going to go straight in and start a Spark application. Now, we have Spark here for Spark Static, Spark Dynamic, but these experiments are used typically if you've got machine learning experiments. Maybe you want to use GPUs. I don't have any GPUs here, but this is basically deciding if I have how many executors. So I'm going to start with 2 executors and 1 driver in Spark. And there's this advanced configuration down here. So this is how I add Git support. So my code is currently available in this Jim Dowling churn Git library. I have an API key from GitHub. I'll show you in a second how to get that. But what the API key is that rather than enter my username and password to connect to GitHub here, on GitHub you can actually create an API key token. And once you've created that API key token, you can store it securely on Hopsworks. And when we start this Jupyter Lab instance, it will use that API key token to check out that repository that I entered there. So I can just show you where the API key token is and how you can create it. We basically go to settings in Hopsworks, and then we have this thing called secrets. And you can see I have a bunch of 3 secrets already, so I can have another one called like GitHub blah, and then I paste in my API token. So how I get my API token, it's in our documentation. If you search for GitHub here, you'll see that generating an API key. You can see here some instructions to tell you how to generate an API key from within GitHub. You basically go to your user settings, personal access tokens, and then you check the boxes you need, and it'll issue an API key. Excuse me. So what's happened now is it's created a Jupyter Lab environment. Jupyter Lab is a new version of Jupyter notebooks. We have support for Git in here. It says I'm not currently in a repo. This is the repo that I checked out. And these are the files I have. So I have this one called create feature group, churn create feature group. I have the create the training data set on S3. I have this one which is train a model using XGBoost and that training data set. And then I also have another notebook to compute good hyperparameters based on the Maggie framework. The other files in here, I have the libraries that tells me what to install, and then finally I have this serving file. And this serving file is actually this one is used if we want to serve the model that we've trained. We're going to serve it on a Flask server, so it's going to run this Python program on the Flask server. So predictions that come in will be handled by this predict method. So it will call on the model that we've trained predict with the input vector. Now in this case, we initialize that model by reading it up from our file system, Hopsfs. So the file will be called, we expect it to be called xgb, so it's xgboost_churn.pickle. So it's a pickled Python file. And you can see what we're doing is we're just copying it from HDFS to the local file system, and there we're using pickle to load that file from the local file system. So this could typically be run, like I said before, on Kubernetes cluster. But let's start out by opening the first notebook. We're going to call churn create feature groups. Let's go back to our project and just check our project telecom and the feature store. So we've only looked so far at the Jupyter Notebook and Python, but if we look at the feature store, we can see that it's empty. We don't have any features here. No feature groups, no training data sets, and no features. So we're going to run this notebook, and it should create a feature group. I'll explain what's going to happen in the notebook. So in this notebook, we firstly import a bunch of libraries. It's going to read the trained data set from our S3 bucket called SageMaker Gym, and the trained data set is called telco customer underscore churn.csv. You can also find available at this URL, and then it'll just get a preview of the data. You can see this is running as a Spark job, so it's a PySpark application. You can see up here as well, it says PySpark. And then we have some data manipulation, just feature engineering. So we saw this example already of looking at the total charges column and replacing spaces with null values. And there's a bunch more steps. I'm not going to go through all of those. There are feature engineering steps and some data processing. So, computing categorical columns from columns in the data frame, numerical columns. And as we move further down, then we get to this line. So this is the line that will create the feature group from our data frame. Telecom is our data frame. This is the name of the feature group. We give it a description, and then we can say whether we're using the online feature store. Is that going to be true or false? So here we just set it to true, so it'll also create this data and put it into the online feature store. This is a new feature we have. We're also able to set tags for, so you can see this here. We're able to set tags for feature groups, so you can have any arbitrary metadata you want. You can define tags, and I defined a tag already called privacy_level. You can think of this as being how we work with data warehouses, and we have metadata catalogs for identifying the different tables that are available. But in this case, I said this feature group, the telecom feature group, its privacy level is PII. It has personally identifiable information. So I'll just, while I mention that, I'll just show you how we can change our set of tags or catalogs. In the administration UI, we can go to the add feature store tags, and here we can just add new tags. So I had this one called privacy level, and I can have another one we'll call like owner, for example. Maybe you can have an arbitrary set of tags here. But if we go back to the feature store now, the project telecom, and we go to the feature store section, well, we should see that the feature store appeared, and it did. And this is our feature group called telecom feature group appeared. Here we can see some overview of the data. We can see the job that was used. So the job was a notebook, so it wasn't actually a job, it was a notebook, so it didn't appear as a job. If you do run a job here, which is kind of a productionalized notebook or a productionalized Python program, that will be coupled in here. And then we can see the schema is quite large for it. But let's look at the tags before we do anything else, because I mentioned those. So I had a tag that was attached, PII, privacy level, and I can create other tags. So in this case, I have owner and privacy level available as tags. I can write this one, my name is Jim, so I'm going to make Jim the owner. And we can see then we have two tags on this feature group. Now, one of the nice things about tagging and this metadata attachments that we make to these feature groups is that they're available for free text search. So if I type in Jim up here, we can find our feature group, and we can see that it's this particular one, the telecom one, and it was in a tag. And I had another one that matched there that I'd been working with earlier. If I type in PI instead of PII, but it's a partial match, we can see that it matched this particular one, the one I just created, where we've got PII. So this is the personally identifiable information. We have this same feature group, by the way, is available in both this churn project and the telecom one. That's my backup one there. So that's great. You can do that free text search to search for features across production, development, staging feature stores. It's kind of a central point at which you can discover features. But then when you want to actually browse features, so you want to do your exploratory data analysis, you go in here, you can look at the feature groups, and here we have one here. We can get a quick overview. Now we have 47 features in one feature group. But we can look at some nice overview of the data. We can look at things like the clustering analysis for the features. There are 47 features here, so for every feature we display the distribution of feature values here. So a lot of these I can see are kind of binary features. Maybe we can find something that's not binary. Most of them seem to be binary, so we get either this many users are here, this many users are here. But what we can see also are descriptive statistics, which are very useful. For any given feature, like total charges, we can see there's 7,000 rows. The mean value is this, and then the standard deviation is this, the minimum value is this, and the maximum value is this. And that's computed for all of the different features in the feature store. That might not be enough. You might want to get a preview of the data that's in there. So you can see you can pull it from either the online or offline feature store. Here we have the first 20 rows, and you can change that to have more rows, and we have 47 columns. So we can scroll to the right to have a look at all of our 47 different features in here. And you can see tenure and multi-charges are kind of non-binary features. So I mentioned before that we had something called data validation. So one thing you might want to do is say, well, I'm going to ingest this data to a staging feature group because I want to validate it before I ingest it and upsert it to the actual feature group. So in that case, what we can do is we can actually define a job that will do data validation on a feature group. So let's do that. And this is going to do it with a user interface. So in this user interface, I can specify predicates on feature groups or on individual features. This one size is on the feature group, and I can say, for example, there's at least 100 rows and maybe at most 100,000 rows. And I can specify that I should get an error or a warning for that particular data validation rule. So now I have one in my menu. I might say for an individual feature, the distinctness of it, for example, gender, there should be at least 2, and maybe you might have 3 genders. And then we're going to change the warning to be error if it's not correct, okay? And then you might, say uniqueness for a given feature, for example, if we pick, customer ID should all be unique. So uniqueness should be at least one. It should be correct. There should be 1.0, 1.0, and we'll get an error if the customer IDs are not unique. Now you can basically add a lot of these data validation rules or predicates on the data. These are DQ rules that you're adding effectively, and then we can click create validation job. So what the job will do is this job will read that data frame or that particular data from the feature group, and then it will apply the feature validation rules, and we'll get an error if there's a problem with that. So a workflow that you might want to have in our platform is we can take a notebook and we can create the feature group, and then we can apply the data validation rules, for example, or we can create a temporary feature group where we'll store the feature, apply our data validation, and if we're happy, we could add a final step to upsert that data to the destination feature group. So one way we can do it is that we can run notebooks as jobs. So let me do that briefly, and we'll have a look at how to do that. So this data is currently in GitHub, and it's checked out to this Jupyter Notebook local file system. So what I'm going to do is I'm just going to copy it into the file system of Hopsworks. Right? So the Hopsworks file system is a HDFS file system called hopsfs. So we can use a HDFS command, HDFS DFS copy from local, and then we can take, for example, this notebook that we had already. So that's not that one. It's called churn create feature group, and then I can copy it into the file system here. So we can see the file system here in datasets. These are the folders that we have. I copied into Jupyter because that's typically where we would have Jupyter notebooks. So I'm just going to copy the path from that. So that's the path to the README file, but I'll just remove that last part, the README. So we'll just paste it into the Jupyter folder. So the path is HDFS projects telecom Jupyter, and that file will be in there. Now later on, I'm also going to do serving. So what I'm going to do is I'm also going to copy in the serving file while I'm at it. So we have this serving .py file, because maybe I want to start serving this model as well. Okay, so now if I refresh here, we'll be able to see that those files should be in here, yes. And we can preview them as well from the user interface, which is kind of handy enough. So we can see this is our notebook, or is this our notebook. So now I can create a job. So let's go ahead and create a job from that. We're going to call it create FG. It's a Spark job or a PySpark job. You can select a jar, Python file, or a notebook. In this case, I'm going to select a notebook. And it's this one. And then we can say, okay, what resources will I give to it? So maybe I'll make it a Spark static application this time. And I don't need to add anything else fancy, and off I go. So now we have two jobs. We have the create feature group, we have the data validation step, and we can pull that together into an Airflow workflow. So what a workflow is basically two steps together, and we'll call this feature engineering, feature engineer, and data validation, DV. And you can schedule it to say run it every day or every month, or if it's an external cluster, you can have an API key, but here we're running it in our cluster, and we'll say you can run it once. So this UI allows you just to basically select jobs, and mostly you can get this to work with just the Hopsworks launch operator. So we have an operator for running these Hopsworks jobs. If you have your own Airflow cluster, you can still call these jobs from your own Airflow cluster as well. So what I'm going to do is I'm going to first select the create feature group step, and we'll add that to our DAG, or directly acyclic graph in Airflow, and then I'll say validate the data, but only run it after we've created the feature group, for example. So clicking on generate Airflow DAG will give me an Airflow program, and then we can schedule and run that Airflow program, and that's it here, and it will run these jobs for us in here. Okay, so that's how to do end-to-end feature engineering with Airflow to orchestrate the execution. So I said I'd also look at creating a training data set, and we have this piece of code here for creating the training data set. You can also create training data sets from the UI, so you can basically click your way to a training data set if you want. You can basically select the features that you want, and off you go. But I'm not going to do that. I'm going to use the notebook. So let me run. I think I'll have to kill the first Spark application because it's using resources. Let's do that. When we click on the Jupyter tag, you can see this application is running, and we can just shut it down. So that's Spark application. I could have done it from Jupyter as well. It also shows me in here the running Spark notebook. So I've finished that one. So I'm going to run all the cells. So this is a very simple program, in fact. And what it does is it's going to check to see if this training data set exists. It's actually checking on our file system, so that doesn't really make too much sense because it's checking on HDFS. We want to write it to our sync SageMaker gem. So now I can realize that I forgot to create my connector to SageMaker, so I'll need to do that before that will work. So to create the connector to the S3 bucket SageMaker gem, I go to the feature store again here, and I go to storage connectors, and then I can click new, and we're going to create one called SageMaker gem, and we'll call it the S3 bucket SageMaker gem in Europe 1. Just tell it where it is, and then I click S3 connector. Now because I started this Hopsworks cluster with an IAM profile, I don't need to put an access key or secret key. I can just give the name of the bucket, and then I can click create. So that's it. I've now got this S3 connector available in my storage connectors, and you can see it's called here. So we can use it then in our application here. So now we can see we got an error saying could not find the requested storage connector SageMaker Gym, but I just created it, so we should be able to rerun it. So let's restart and run all cells. Now in this case, what it's going to do is it's going to just go to the feature store to get the telecom feature group as a data frame, and then save that whole data frame directly. But often what you would do is you would join features together into a data frame and then save that data frame. But in this case, it's going to now use the sync SageMaker Gym as the sync, which is our bucket. And then after that, you can decide to compute statistics. If you're going to use this training data set, the results of it, these descriptive statistics for an online model. So if your online model is going to monitor its performance, descriptive statistics in the feature store are very useful, because what you can do is you can compute the descriptive statistics over the incoming or live data and compare it with these descriptive statistics computed here on the training data set to see if there's a deviation between them. So we call that data drift between the live data being used to make predictions on the model, and this is the data we've used to train the model. So because those statistics are available in the feature store, you don't need to recompute them again when you go to your serving infrastructure, which is very nice. Now you can see at this point it completed successfully. It created the training data set on S3, and then we can train our model on S3. So in this particular example, we can see off it goes. We can just kind of skip through it. It's basically going to use XGBoost to we can run it as well, actually. So to run it again, I'm going to shut down the other Spark application that was running. We can do it from there, and then we can just run it from here. So run all cells. So this example, what it's doing is it's getting our feature group as a data frame and then trains a model using XGBoost. And then what it will do is it will, in this case, we can see it's going to give us a classification report for the accuracy of the model, and then it'll save that model to the model registry in Hopsworks. And we can see the name is XGB_reg. So actually, I'm just curious if we open this serving pod, if that name was correct. Okay, so I can see, yeah, there's the path to the model. And we can see actually a slight mistake here, that the names didn't match up here. So that's where dry code would have been obviously it's, beneficial. I'm going to copy that back because otherwise that won't work. So you can do a -F flag here to force the overwrite. Okay, so let's go back and look at that file just to make sure that that's correct. Now if we go to our Jupyter notebook, this is the model serving file we're looking at here. And just to make sure yeah, so it's xgreg.pickle and xgreg.pickle. Okay, so the training should be done, I guess, at this stage. Let's have a look. It started the Spark application. It did the training. This is our report with an accuracy score, and then it saved the model to the model registry in Hopsworks, and that seemed to go fine. So let's have a look at the model as it gets exported. So the model should have been exported here. And we can see, yes, our XGBoost churn model is available. You can use this directly from a Spark application, and we can see the accuracy is not great, but you can improve on that. The code for the model, the actual and the experiment for it are accessible from here. So this is the code for the model. This is the pickled Python file. So you can use a batch application that can use the REST API to get this directly. This is the program that was used to train that model. So we get a nice snapshot of that and a snapshot of the environment, the Conda environment used to train that model. Now, what we can do is we can actually start that model serving by going to the model serving part. Now, the model serving basically gives you two options, TensorFlow or scikit-learn. Scikit-learn will work because it's basically a Flask server. We need to specify this Python script that I just edited briefly, but then we can also specify the model serving name. So let's give it a name, just XGBoost. And what we'd like to do in this case is any predictions made on the model, we'd like to log them to Kafka topic. And we can see there's a Kafka option up here, which we'll look at after we create the serving code. So if, for example, you're serving a TensorFlow model, you can just select the protocol buffer file. You don't need this serving.py file. So this particular model is available here. You can use APIs to obviously create these, deploy models to model serving infrastructure and start them. You can also use the UI. So once it's started, you can get some detailed information. Here we can get the endpoint that we use to make predictions with. We can go to Kafka to look at our topic, and you can write a program which will read from this topic. And with that endpoint, we can actually have an external application make predictions on the model. And that external application, what it can do is it needs an API key to make the calls on that REST endpoint. So you can go to your username here and to settings and create an API key token. And we might call this one we'll call it XG, we'll call it my pred. Okay, and my prediction model, and we need to select API scopes for it. So we'd like to be able to call it inference calls and within a project. So you can create that API key, copy that API key token, and then we have the endpoint for our REST applications. So they just need those two pieces of information, the API key and the REST endpoint, and then they can send their input feature vectors to the model for real-time model predictions. Okay, that's pretty much the end-to-end demo of going from the raw data on S3 to creating our training data sets and training models and then serving them. So let's move back to finish up. Okay, so that's what we covered. The churn model for telecom users, the code is available and the data set's available on jimdowling/churn on GitHub. You can reproduce this on Hopsworks.ai by creating a cluster there. If you want to find out more about the Hopsworks feature store and the Hopsworks platform, you can contact us through our website, logicalclocks.com. You can follow us on Twitter, and you can also communicate with us via our documentation. We have a community site, Hopsworks Community, and you can also, of course, like us on GitHub and follow us on GitHub, where the open source version is available. Thank you, and have a great day.